Hello everyone, my name is Sumedha and today we'll discuss oscillation. In this chapter we'll discuss different type of motion. So let us start with periodic motion. Periodic motion. अब periodic motion के name से ही पता चल रहा है that it's related to time period. So this is a motion in which particle repeats itself after a certain interval of time. Motion of particle repeats itself after certain interval of time. Example: motion of planets around sun. मोशन ऑफ प्लैनेट्स अराउंड सन. सन के अराउंड जब प्लैनेट्स मूव करते हैं तो वो एक पर्टिकुलर इंटरवल ऑफ टाइम के बाद अपना जो पाथ है वो दोबारा से सेम पाथ सेम मोशन रिट्रेस करते हैं. तो दैट्स कम अंडर पीरियोडिक मोशन. नेक्स्ट वी हैव ऑसिलेटरी मोशन. ऑसिलेटरी मोशन. In this motion, the particle oscillates to and fro about a fixed position. Particle oscillate, or we can say particle displaces to and fro about a fixed position. This is called oscillatory motion. For example, अगर मेरे पास पार्टिकल है तो वो जो पार्टिकल है वो मूव करेगा, डिस्प्लेस होगा इन दिस डायरेक्शन देन इन दिस डायरेक्शन. तो जो उसका मोशन होगा वो दोनों डायरेक्शन में रहेगा. दैट मीन्स द मोशन इज टू एंड फ्रो. तो जो ये पार्टिकल होगा हम कहेंगे दैट पार्टिकल इज ऑसिलेटिंग एंड द मोशन इज कॉल्ड ऑसिलेटरी मोशन. Next we have harmonic functions. Harmonic functions are those in which trigonometric terms are included with amplitude. Trigonometric terms are involved. For example, I say the displacement of a particle is a sine theta, where a is the amplitude, or I can write it as a sine omega t, where omega is the frequency and t is the time period. Now what is amplitude? Amplitude किसी पार्टिकल का क्या होता है? The maximum displacement a particle can show. Amplitude is maximum displacement of particle. एंड फ्रीक्वेंसी कि वो किस फ्रीक्वेंसी के साथ डिस्प्लेस हो रहा है या ऑसिलेट हो रहा है या वाइब्रेट हो रहा है. दैट इज द फ्रीक्वेंसी ऑफ द पार्टिकल. So time period is the period in which the particle repeats itself. Period after which the particle repeats itself. We denote time as 2 pi upon omega or time period as 1 upon n. If we are talking in terms of angular motion, then omega is angular frequency and this here n is linear frequency or simply frequency. So now what is frequency? Frequency, we define frequency as number of oscillations per second is called frequency, or we say n is equals to 1 upon t, where t is टाइम पीरियड. अगर हम ग्राफ से देखें, सपोज माई पार्टिकल इज एट हेयर और वो ऑसिलेट कर रहा है और ये ग्राफ बना रहा है. Here it's time and here the displacement. So particle ने यहाँ से start किया. After completing this one cycle complete, this is half cycle in the positive and this is half cycle in the negative. So this is complete one cycle. One cycle complete करने के बाद वो दोबारा से उसी point पे आ गया जहाँ से उसने start किया था. That means now it's repeating its motion. This is my second. So from here to here, this is one oscillation in 1 second. This is one oscillation and again this is one oscillation. So these were the introduction to basic terms. Now we'll study simple harmonic motion. Simple harmonic motion. So simple harmonic motion is the simplest form of vibratory or oscillatory motion. We have two types, one is linear and one is angular. In linear, we have example of spring mass system, in which we have a spring and mass is attached. In angular, we have an example of simple pendulum. That is, a pendulum is attached and it's tracing a path like this. So now in linear, we have force which is directly proportional to minus of x, that is x here is the displacement, and in angular we have torque that is proportional to minus of theta, where theta is the angle. Here acceleration is directly proportional to minus of x, and here alpha, that is acceleration, is directly proportional to minus of theta. So these are the two types. Now we are studying simple harmonic motion, so we'll write x is equals to a sin omega t, or we can write x is equals to a cos omega t, where x is the displacement, a is the amplitude, omega frequency and t टाइम. अब हम हार्मोनिक मोशन की बात कर रहे हैं, तो वी हैव कंसिडर्ड हार्मोनिक फंक्शन विच आर इन द फॉर्म ऑफ ट्रिग्नोमेट्रिक फंक्शन आइदर साइन और कॉस. सो वी हैव डिस्प्लेसमेंट. नाउ वील कैलकुलेट velocity of simple harmonic motion. From the definition of velocity, we know velocity is rate of change of displacement dx upon dt. So we'll do d by dt, substituting the value of x from here, it is a sin omega t. So v is equals to a as it is, because a is constant, d by dt of sin omega t. So derivative of sin is cos omega t and d by dt of omega t. So d by dt of omega t will be omega, so I'll get a omega cos omega t. This is the velocity. Now from the trigonometric relations, we know sin square omega t plus cos square omega t is equals to 1. So we can write cos square omega t is equals to 1 minus sin square omega t. Now cos omega t is equals to under the root 1 minus sin square omega t. Now again from this equation, I can substitute sin square omega t as x upon a. So cos omega t will become 1 minus x upon a square, or cos omega t is equals to under the root a square minus x square upon a square, or we'll just say let it in this form only. Now substituting the value of cos omega t from here to the value of velocity, we'll get v is equals to a omega under the root 1 minus x upon a whole square, or a omega under the root a square minus x square upon a, which is equals to omega under the root a square minus x square. So this is the value of the velocity. So we get velocity is equals to under the root a square minus x square omega. Now squaring both sides, we'll get v square is equals to omega square a square minus x square. Now from here, v square upon omega square can be written as a square minus x square, or we can say v square upon omega square a square is equals to 1 minus x square upon a square, which is equals to v square upon omega square a square plus x square upon a square is equals to 1. So this is a form of ellipse. That means जो सिंपल हार्मोनिक मोशन में पार्टिकल है उसके वेलोसिटी की इक्वेशन क्या शो कर रही है? दिस इज अ फॉर्म ऑफ एलिप्स. So this is the velocity of the simple harmonic motion. Now we'll differentiate velocity and calculate acceleration. So we have calculated velocity from the equation of displacement. Now we'll calculate acceleration. So acceleration is dv by dt. Substituting the value of velocity from here, we'll get d by dt of a omega cos omega t. So a omega is constant, so d by dt of cos omega t. So we'll get a omega, differentiation of cos omega t is minus sin omega t, and differentiation of omega t is again omega, so we'll get omega square. So we'll get acceleration is equals to minus a omega square sin omega t. Now we can write acceleration as a sin omega t. This term is equal to displacement. A sin omega t is equals to displacement. So we can write acceleration is equals to minus omega square x. So after calculating velocity and acceleration for SHM, we'll calculate potential energy for simple harmonic motions. Potential energy for simple harmonic motion. Now we know F is equals to minus du upon dx, where u is the potential energy. So we can write du as minus f of dx, say equation number 1. Now from here As f is directly proportional to minus x, f is equals to minus of kx. Substituting the value of f here, we'll get du is equals to minus of kx dx. Du is equals to kx dx. Integrating both sides, integration of du is equals to integration of kx dx. So integration of du will be simply u, that is the total potential energy, and integration of kx is k is constant, so integration of dx, u is equals to k x square upon 2. So u is equals to half k x square. So this is the expression for the potential energy of simple harmonic motions.